the curvature thing on the left hand side, if you only have an electromagnetic field in some region of space-time which does not contain any matter, would that suffice to actually give you a curved background?
Yes, that's it. That should curve space. Because electromagnetic field is a source of energy, right? So non-zero energy density, and that will produce curvature of space-time.
Anything non-zero on the right-hand side will produce a
right, so it's, I mean, the actual effect is very small because as I was describing, once that to see how much the electromagnetic field will contribute, it contributes energy, right? Whereas the actual source of gravity that you think of in non-relativistic system is matter, right? So you have to divide by a factor of c square, right, to see this as a source of gravity. And so there is 1 over c square coming in there. Right? And then you saw also that when you convert from the usual gravitational potential to metric, there is another factor of 1 over c square. Right? So when we actually try to see what an electromagnetic field in conventional units will correspond to in terms of curvature of space-time, that's very, very small. Right? It's like 1 over c to the 4, but nevertheless this effect is always there. Right? So there will be a curvature of space-time produced by electromagnetic field.
Sir, we have not shown that the uniqueness of that the Einstein's equation will give you a unique metric for experiment.
No, it need not.
It need not.
It need not give a unique metric. In fact, even in the absence of any source, right, there are solutions to Einstein's equations which are called gravitational waves, and that's not unique. Right? It's not true even for Maxwell's equations, right? Because if you just write down the Maxwell's equation in flat space, right, it doesn't have unique solution. It has electromagnetic waves, right, which are characterized by their own polarization vectors, directions, and so on. So there is no reason to expect that given an energy momentum tensor, the solution to Einstein's equation is unique.
But sir, when we are solving, like currently in this situation, like in spherical symmetric case,
Yes.
you are getting a very unique.
Yes, because you are requiring time independent solution. Right? So time independence puts strong constraint. But otherwise, there is no reason to expect unique solution.
So there is a second order differential equation.
Second order partial differential equation.
Second order partial differential
That's
equation. If you get out the constant, then we.
Yeah, so the point it depends on the structure of the equation. So here, for example, at a given time, if you specify the metric and its derivatives completely, then under certain circumstances you can evolve it forward in time. Okay? But you have to do it at every point on a space point for a given value of time.
This is just a boundary condition.
Yeah, exactly.
So under a boundary you can find a equation.
Yes, but it's not always true. There are conditions under which it will happen. Right? But near flat space time, right, this is what we expect, that if we are given the initial condition on a given time slice, right, everywhere in space, then you should be able to evolve it forward and see what the metric looks like at a future time.
So under invariance under rotation, we had expressed everything as functions of r.
That's
But for invariance under rotation, we had that each coordinates square should remain invariant. So we had x1 square plus x2 square plus x3 square that we put to r square.
That's
Couldn't we have some function, some new quantity, x1 square plus x2 square plus x3 raised to power 4? So this should also remain invariant under rotation.
No, that is not, because under rotation, that is not invariant, right? Because we define the rotation transformation as xi going to xij, rij times xj. Right? So this is usual rotation in, say, x1, x2, x3 goes to some orthogonal matrix as x1, x2, x3. Right? So now x1 square plus x2 square plus x3 to the 4 is not invariant under rotation. Right? In fact, the only scalar function that you can construct out of x1, x2 and x3 is r, which is square root of x1 square plus x2 square plus x3 square,
No
and any function of r.
There is no other possibility except.
No, just think of it flat three-dimensional space-time, right? Space, right? If you have a vector, because this transformation is like a flat space transformation, right? So mathematically, the problem is exactly the same as finding a rotational invariant combination of x1, x2, x3 in flat space. And there the only rotation invariant combination is a radial distance, right? Anything else is a function of r. Okay, and this you can prove in general, right? That the only way to construct rotation invariant object out of x or out of a vector is just r and this function. Yeah, so that's the reason why this is, r is the only possible. Otherwise, if it has another function, right, you could have written as a function of not one variable but two variables, right? Two of those combinations which are invariant. But in this case, you can show that there is no other possible function of x1, x2, x3, which is independent of r, right? Which is not a function of r, and which is rotation invariant.
Sir, the two space points which I will treat that they are being rotated by some transformation r.
Yes.
Should be taken as a distance, the things which keep the distance same, right? But right now you are not having
No.
metric.
So that's the point. So we are not defining rotation as something that keeps distance fixed. Okay. Rotation you are thinking of abstract as a transformation, okay, on space-time coordinates, right? As I said, there is an invariant way to define what rotational isometry means. But you can think of it as a group. It should be a group of matrices which have this structure, right? A group of matrices which has a structure of 3x3 orthogonal matrix. Okay.
So there is one frame in which you have under root x1 square plus x3 square.
So that has nothing to do with distance, right? Because the metric is not flat, right? But nevertheless, it is true that the square root of x1 square plus x2 square plus x3 square remains invariant under this transformation. Okay? So don't think of r as a distance, because r is certainly not a distance, right? Even after we got the final form of the metric, right? dr square has something multiplying it, right? So clearly it's not distance. But r is just some function of x1, x2, x3, right? That's the way you should think of it. Yes.
For some TVM,
Yes.
there will be two solutions of Einstein equation.
Yes.
And around that TVM, one will fill which type of space-time effect?
There will be different space-time. Okay? If there are two different solutions, as I said, even if T mu nu is 0, you can construct solutions to Einstein's equation in the form of gravitational waves, right? They will describe different kind of space-time, right? Depending on the parameters that the gravitational wave carries, right? How much is the amplitude? How much is what is the polarization? In which direction it is moving? Okay? So T mu nu does not fix the solution. Different solutions will describe different space-time geometry. Yeah, so there is no one-to-one correspondence between given a T mu nu and the space-time geometry. Right? You also have to say what are the initial boundary conditions you have to take. But this is no different from electromagnetism. Right? Given a point charge, it doesn't specify the electric field, because even in the absence of point charge, you can have electromagnetic wave propagating, right? Which creates electric field. In the presence of a point charge, also you can have a Coulomb force, of course, but on top of that, you can superimpose electromagnetic wave propagating, right? So that's a different electric field, right? Which you can also ascribe to the electric field of a point charge, because the only source here is a point charge. Okay, any questions? So is this point clear that this R that we introduced, right, is just this object, right? Don't give it any other physical interpretation. Okay, it's by definition this object. Okay. And the spatial property it has is that this remains unchanged under a transformation of this kind. So multiplying by any function of R does not change the rotational property of the corresponding object. Okay, if it transforms in a certain way, when you multiply by some function of R, it will transform exactly in the same way. Okay, so let me write down some of the main points that we discussed last time. So the first thing is that after doing a lot of manipulations and change of coordinates, we brought the metric in some standard form, which we started analyzing. Minus I of rho dt square plus I of rho d2 square plus d2 square and the So this is the general parameterization of a rotationally independent, time independent metric. Then we started analyzing what Einstein's equation imply for this, and we are studying source-free Einstein's equation because the point charge not worry about. We look at the equations away from the origin, okay, where the point charge is sitting. And there we found that this, when you calculate, when you try to solve Einstein equation r when equal to 0, this is automatically satisfied. Well, we didn't show it, but you are supposed to show it. Automatically satisfied for nu not equal to 2. So the only non-trivial equations come from the parts where mu and nu are equal. So r tt, r rho rho, r theta theta, and r phi phi. And then we wrote down explicit expressions for r these components. So r rho rho was psi double prime psi minus 1/4 psi. And in all these equations, prime means zero rate. And the idea is that we have to now solve for all of these individually equal to 0. Okay, because those are the non-trivial Einstein's equations. Then we also analyzed this equation psi times r rho rho plus chi times r dt equal to 0, and this we saw has a solution which is psi chi equal to constant. And then we said that by scaling time coordinate, scaling t, we could change the value of the constant in principle. Okay, and depending on whether psi chi is positive or negative, we can bring it to plus or minus 1.
We could also have 0. The constant could also be 0.
The constant could also be 0. Then of course it will remain 0. But that means either psi or chi should be 0.
If the constant is 0, either psi or chi is 0, that's directly an element of the metric, right?
Yes.
In this
so the metric will be singular.
The metric will be singular.
As a formal solution, of course, it still makes sense. But if one of them is 0, then of course, then you can say the metric is singular, right? In one direction, there is no distance. But you can actually fix it uniquely to be 1 from physical considerations. After all, we want this metric to represent the field of a point mass, right? So we expect that far away from the point mass, which is rho goes to infinity, this should reduce to a standard Minkowski metric, right, as rho goes to infinity. So which means psi of rho should approach 1, chi of rho should approach 1. Okay, and this of course has the correct form.
Sir.
That means we want, okay, we have to scale t for this, but we want that after appropriate scaling of t, the metric must be in a form where psi rho times chi rho approaches 1, psi rho and chi rho approaches 1 as rho goes to infinity.
So, we have, as we have defined this rho, it's a complicated function of r.
That's right.
And what we know that r is not the real distance from the point particle, as it's
Yes.
not distance in that space time.
That is true.
So how we are confirming that rho goes
Basically,
to
the point is,
infinity?
if you look at the large R region, right?
Hmm.
We went to the complicated field redefinition, but in the large R region, the relation between rho and R is really rho equal to R. Right?
Yes.
That's one of thinking of
But-
it. Another way of thinking of it, we have this metric. Right? Now we have to have some asymptotic region, right?
Yes.
We declare it to be as rho goes to infinity. Right? If rho goes to 0 as the asymptotic region, you just change rho to 1 over rho
And then redefine.
and redefine the metric. Right? That will just redefine our psi and chi.
Yes.
Okay. So you can, given this metric, you can always choose to define rho equal to infinity as a region at infinity. Okay, so that's a choice, right? You could have taken a different approach where you call 1 over rho, but then of course this will not match. Right?
That
So
section already matches.
yeah, in a sense this already fixes that it's rho goes to infinity, that should be the asymptotic region. Right? Because rho goes to 0, this term will go to 0. Right? So it's not consistent to interpret that or any other rho as the asymptotic region. Right? Because at least we know that the theta phi sphere should go, the radius at infinity, the surface at infinity should grow as rho square, as rho goes to infinity. Right? That's the standard radial distance. So that basically fixes rho, at least for far away, rho should be the asymptotic, the distance, what we normally call the radial coordinate. Okay, so with this we know that psi and chi should go to 1, but psi chi of course is constant, right? It doesn't depend on rho. So if psi and chi goes to 1 as rho goes to infinity, then we know that psi times chi should be equal to 1 identically. Okay. If psi times chi had been minus 1, okay, that's a possible solution to the Einstein's equations. But this will tell us that either both psi and chi are, that will tell us that either psi is negative, chi is positive, in which case the metric will have Euclidean signature, right, which is not what we are looking for. See, if psi is negative and chi is positive, then its eigenvalues are 1 plus 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 plus, right? So that's certainly not the Minkowski space-time that we are looking for, the asymptotical Minkowski space-time. Or if psi is positive and chi is negative, then the eigenvalues are like 2 minuses and 2 pluses, right? So it describes a space-time with 2 time-like coordinates. That's also not what we are looking for, right? Asymptotically at least it should become the standard Minkowski space. So that basically fixes this constant to be positive and we can take it to be 1. So psi chi is equal to 1. So we'll work with this. By choosing psi chi equal to 1, we are already guaranteed to some extent that asymptotically this approach is the correct metric. Yes.
So, irrespective whether we scale our time coordinate or not, so
Yes.
psi chi is 1.
Well, the point is that you may, if you just try to solve the differential equation, then psi chi, what that means is that this time t that you have chosen is not the time t that you will refer to in the Minkowski space. Right? So you have to rescale this time t to match with the Minkowski time, the standard time that we are familiar with in Minkowski space. So that basically will scale back psi chi equal to 1.
Even after putting psi chi equal to 1, we
Yes.
can always have a time redefinition when this new psi chi will go to something.
Yes, but that time redefinition will send this metric to something that doesn't look like a standard Minkowski metric.
Yes. So the idea of putting the constant into the by redefining the t is much more general than putting the infinite.
No, it's not much more general. You can always do this by rescaling t. Okay? But the motivation for doing this okay, is that we want this metric to eventually look like Minkowski matrix at far away. Right? So if you set this equal to 2, okay, you know that whatever you do, the metric will not look like the standard Minkowski metric, which has all minus 1 and plus 1, all plus 1 minus 1 and all plus 1s, right? Okay? So you have to rescale anyway. Right? We know that if you did put psi chi equal to 1 but psi chi equal to 10, then eventually you have to rescale t back so that you look like it, so the metric looks like the standard Minkowski metric. So you might as well from the beginning do this rescaling so that this product at least we cannot guarantee at this stage based on what we have that individual psi and chi should approach 1, right? That's something what you want at the end, but that's not guaranteed. Okay? But at least what is guaranteed is that psi chi is in our hand. Okay? So, and we know that psi chi should go to 1. So you might as well set it equal to 1 by rescaling t at this stage. Okay? We know that after this we cannot rescale t anymore. Okay? You can rescale t, but that will not help us in going towards Minkowski, because if we rescale t, psi chi will change. Okay? And that means that whatever you do that metric will not look like a Minkowski metric. Right? Because for Minkowski metric, psi chi should go to 1. Is this clear?
So the time redefinition is a compulsory step to put the
Yeah, when the what allows us to go from this to this is time redefinition.
Yes.
Now, why we want to do this? That comes from the motivation that we eventually want to find a metric in which psi and chi should approach 1 as a goes to infinity. And that means that psi chi should approach 1. Right? If psi and chi individually has to approach 1, then psi chi better approach 1. Okay? So that justifies why we want to make this redefinition at this stage. Okay? To set psi chi equal to 1. If you didn't want it, you could have kept it as some constant. There is some more terms in the equation. At the end, we have to rescale anyway. Okay? Because what the metric that we get may not look like standard asymptotic Minkowski, Minkowski metric asymptotically. You have to rescale t to bring it back. We know that if you work with psi chi equal to 10, you can never get the standard Minkowski metric. Okay? Because for standard Minkowski metric, psi chi is equal to 1 at infinity. Is this okay? Okay. So after this, things are simple. Okay. So let's look at the r theta theta equation. So r theta theta equation equal to 0. This gives us minus 1 plus, let's express everything in terms of psi. Okay. So this becomes rho over 2 times psi. Now chi prime over chi is minus psi prime over psi, right? Because psi chi is constant. So this becomes 2 psi prime over psi plus psi equal to 0. Okay, because 1 over chi is psi. So this gives you minus 1 plus rho psi prime plus psi equal to 0. Or d rho of rho psi equal to 1. Okay, because this is d rho of rho times psi. So this tells us that rho psi is equal to rho plus a constant to psi is equal to 1 plus c over rho. And then chi is 1 plus c over rho inverse. Is this okay? So now we have solved the equation completely up to this constant. Now we still have to check. Okay, so first of all, r phi phi is automatically 0 because it is just proportional to r theta theta. Okay, we don't have to do anything here. But we have only worked with one linear combination of this, which is here. Right? That we have set equal to 0. The other linear combination you have to check, right? Or if you equivalently you can say that you have to check that r rho rho is 0. Okay, because that will guarantee that r t t equal to 0 because of this equation. Okay. So I'll leave it as an exercise. Let's check. This is R rho. Well, it's actually not very hard because this is 0 anyway, right? Plus chi psi equal to constant, so basically you have to take sum of these two. Psi double prime psi plus 1 over rho psi prime over psi. So this now solves the Einstein's equation. Okay, in the specific context. So let me write the solution then. So ds square minus 1 minus 1 plus 0 over rho dt square plus 1 plus 0 over rho inverse d square plus rho square and b plus square.
Sir,
Yes.
just one question that means this equation that we obtained psi r rho plus chi r tt equals to 0. There was no independent way of reaching to this equation. We only reached it by the fact that r rho is equals to 0 and r tt equals to 0. So the combination would be equals to.
No. There could have been. Is there? You have to check the consistency. So this equation does not guarantee that this is equal to 0.
Yes, it means given this equation, it does not guarantee. But
Yes.
we reached at this equation using only these two factors, and there was no other
Yes, exactly.
way we could have. Means there was no other given thing that could lead us to this equation. If we do not derive this equation independently of the condition.
No, this equation is derived from the Einstein's equation. Right?
These equations are derived.
Yes. So this equation,
Condition
if r rho is 0 and r tt is 0,
is one solution.
no, not a one solution. See, the metric that you are looking for has to satisfy both r rho equal to 0 and r tt equal to 0, right? And hence, this combination also must vanish. Right? That's what it, so basically what are you doing? I mean, forget about this. Okay? That we have these 4 equations you have to solve. Okay? We can solve them in different orders. Okay? We just chose to look at first the equation where this times psi plus this times chi is 0. And if there are 4 equations A, B, C, D, okay? A equal to 0, B equal to 0, C equal to 0, D equal to 0. I can always choose to first solve for A plus D equal to 0. Right? Then solve B equal to 0. That's what you are doing here. Right? I first solved this particular linear combination equal to 0 and then went ahead and solved the others.
And then I'm checking that indeed A equals to 0 is also consistent.
Exactly. Because the point is, we have only solved A plus D equal to 0, right? And B equal to 0, right? That is plus C equal to 0. We have not checked, for example, A minus D equal to 0, right? So this is like assuming, proving that if you take a minus sign here, then that should vanish. And that is another way of doing this. If you put a minus sign here, basically what will happen is that last term, let's see, minus sign, this term will cancel out. And the others will remain, they are in fact identical. Okay, and you have to check that those, that is
I prime by chi plus I prime by psi is already 0.
yes, that's right.
So that is trivially 0 if I take psi r rho minus chi r tt.
Yeah, so this is 0, but the difference between these two, so you are now taking psi times this, right? Chi times this and taking the difference. That difference you have to take into account, combine with this, okay, and check that that is 0. Okay? Which is equivalent to checking that this is individually 0, because if this is 0, then it's automatic that RTT will also be 0, right? From this equation, because chi is not identically 0. Okay? So you can arrive at a solution by following any route that you like, but at the end you have to make sure that if to declare that that is a solution, all the equations must be satisfied. Okay, and that's what I am saying, that these are automatically satisfied because these equations you have actually solved. This is not guaranteed because this equation you have not solved. Right? So you explicitly check that this equation holds, and then this holds because we have made sure that this is satisfied. Any other questions? Okay, so in this form now we see that as rho goes to infinity, indeed the metric approaches the standard Minkowski metric because this becomes minus dt square, this becomes 0 square. Okay. We had guaranteed by choosing this constant, we had guaranteed that the product will go to 1. Okay, but we didn't impose explicitly the requirement that the individual case should go to 1. Okay, that comes out automatically. Okay, if there in fact if this is 2 and this is half, it doesn't satisfy Einstein's equation. That's why we didn't get such solutions. Okay, if this is 2 and this is half, that's not Minkowski's case. Okay, and it in fact doesn't satisfy Einstein's equation. So Einstein's equation actually forced us to get both approaching 1. Okay. Now we have not solved the problem completely because we have to now find the interpretation of this constant c. Okay. So this is the analog of what we did for Newtonian system. We first solved del square phi equal to 0. Got the result as phi equal to minus c over rho. But then we have to identify what that c is in terms of the mass, right? The mass was sitting at the origin, and we got it by saying that we integrate, okay, and we integrate this at the boundary and equate it to what we expect, and that's the way we identify the constant c. So here we will follow a slightly different route by making correspondence with the corresponding Newtonian result. So you already know from Newtonian result what we expect, and we are going to use that. So let's look at this far away from the origin, but we don't set this equal to 1, we keep at least order 1 over rho term in this expansion. Okay, and see what we get. So G naught naught as rho goes to infinity, as rho becomes large.
So, our rho term is the second chi because psi is already with us from
Pardon?
yes, we will keep 1 over rho in chi term because psi is already just 1 over rho term.
No, psi is this.
Yes, yes.
1 plus c over rho. Right? Yeah, so you expand for large rho. Right? Yeah, so here you have to expand, here you, this is exact. Okay? But let's look at large rho anyway. Okay? Because that's where gravity is weak. Right? Because that's where we need the large rho because if you want to compare the Newtonian result, right, you need weak gravity, right? The matrix should be almost flat and plus corrections. Okay? And of course the time independence is automatically built in, so the fact that the matrix should be slowly varying, that condition is automatically satisfied, right? Everything is time independent. But to make correction of Newtonian results, you have to also declare that G mu nu is close to eta mu nu. Okay, and that you can see happens for large rho. Okay, this doesn't look like eta mu nu, but for large rho, this you can rewrite in the Minkowski, in the Cartesian coordinate.
So from Einstein's equation, now there is no such boundary conditions to help you to fix. Is it like that?
Well, it's to directly integrate Einstein's equation is difficult because it's non-linear. Okay, so we'll make correction through Newtonian equation system.
But but by principle, it should give you a c value also.
Yes, it will, except that as I said, the Einstein's equation, because they are non-linear, right, by knowing what the source is at the origin, you may not know what asymptotic behavior will expect. Right? In fact, the only way to the natural way to define mass or other charges in Einstein's equation is by integrating at infinity. Okay, not by looking at what delta function source you have. Because the delta function source, right, the gravity itself can supply to mass. So what the mass of this system is really understood by going at infinity. Okay, so you define mass of an object by seeing what kind of influence it has on a test particle at infinity. Okay, so the only relevant information is the field at infinity, right, not what happens at the center. Okay, so for large rho it becomes -1 minus C over rho. But G naught naught, if you recall, we had defined as eta naught naught plus H naught, right? G mu nu was eta mu nu plus H mu nu. We had defined a small field fluctuation. So by comparing, we see that H naught naught is minus C over rho. On the other hand, we have seen that H naught naught can be identified as minus 2 phi. Okay? This phi is yet a different phi. This is a Newtonian potential. Yeah, this is when you compare general relativity with Newton's gravity. The condition under which you could make this comparison are valid here because you are dealing with time independent system and we are looking far away from the origin where the metric is almost eternal. So comparing these two, we get that phi equal to C over 2 rho. But you know that for a point mass at origin r equal to 0 in Newtonian gravity gives phi equal to minus g m over rho at rho equal to 0. Okay, let me come to rho as a regular variable.
So you should take a special distance
Between, since the metric is becoming flat,
okay.
the spatial distance is just the ordinary Cartesian distance.
So if you put it, you will get a second order C.
Exactly, yeah. Okay, so this rho is the distance as measured from large non-asymptotic observation. So if we have compared these two, we see that C is given by minus 2 gm. So let me again explain what it means. So what this says is the following: that if we take C equal to minus 2 gm, then this particular solution at large distance, okay, suppose you did probe the thing very far in the interior, but you are only seeing at large distance, okay, then this solution for C equal to minus 2 gm will look as if there is a point mass sitting at the origin, okay, and the point mass has value m. Whether there is really a point mass at the origin, we don't know. But from far away, it would look like as if there is a point mass at the origin. And as I said, this is the only way you can you define concept of mass or energy in Einstein's theory. Okay? That you always define charges by measuring what they produce at infinity, okay, rather than what's happening in the interior. Okay? This is analogous in electromagnetism. Okay? That you measure the electric charge, you can measure the electric charge as a point source. Okay? But another way of measuring the electric charge is by saying what happens at infinity. Okay? Because that gives the total charge, okay, that is enclosed by that system.
But sir, in comparing your H naught phi to your solution of the Newtonian potential,
Yes.
you only allow two possibilities, either a point charge or a spherically symmetric distribution.
Exactly.
That's right.
Yes. Yeah. So here also it can be a spherical symmetric distribution.
Or a
Right.
point charge.
Yeah, or a point charge, right? So this point charge is the limit of spherical symmetric distribution, right? Yeah, so you can say there is a spherical symmetric distribution, okay, and this So this solution, right, let's imagine if it's a spherical symmetric distribution, you don't expect that this will hold all the rho equal to 0, right, because once you reach that mass distribution, the energy momentum tensor will be non-zero, right? So you have to solve a different set of equations. Okay. But outside that spherical distribution, this will be the field, okay, and from far away it would look like as if the total mass that is contained is given by this M over here, right, where M and C are related by this relation.
So, one question.
Yes.
So when we solve this equation, Einstein's equation, the way we constructed the equations was that T mu was 0.
Yes.
T mu equals to 0.
T mu equal to 0 outside certain distribution, right? That this solution T mu equal to 0 would mean that this can be trusted all the way to rho equal to 0, which you may not want to trust, right? Because at rho equal to 0, this is singular anyway.
One question was that I started with a condition that there is no source.
No, there could be source inside rho equal to rho naught for some arbitrary rho naught.
Oh,
Okay. This solution will be valid for rho larger than rho naught, right? We didn't have to assume that there is a source anywhere. It's that this solution will be valid only in those regions where there is no source. Right? So this solution can be equally well be thought of as the field, that gravitational field that is produced by a spherical distribution of charge of mass outside that region. Is this? Yeah?
Sir,
Yes.
sir, there can be different point mass other than the for which we are considering at large distance, because we are saying that by knowing the behavior at infinity, means very far from that point mass, we will know about the mass at the.
No, that's the definition. So we define mass by saying that what kind of gravitational field it produces at
But
infinity.
you are seeing at the large distances, so in between there will be other point mass which will be contributing to that thing.
But if there are other point masses, they will destroy spherical symmetry. Right? If there is a point mass here and a point mass there, they will destroy spherical symmetry. There can be spherical symmetric distribution of masses.
So that contribution will be due to both.
Yes, exactly. So this measures the total mass that the system encloses, right? And that mass has to be enclosed inside a region where this is valid. This solution is valid. So this solution has been obtained by assuming that there is no energy momentum tensor, right? Now let's suppose that there is energy momentum tensor, but inside the region rho equal to rho naught. This is still a perfectly good solution for rho larger than rho naught. So you will conclude that this describes a. So suppose we say that the solution is this for rho larger than rho naught. We don't know what the solution is inside rho equal to rho naught. Then what will be the conclusion? The conclusion will be that there is a distribution of mass inside rho equal to rho naught, and this is the field that is produced by that mass distribution. We don't know how it's distributed, where the masses are. Okay, it produces spherical symmetric gravitational field, and the total mass that is enclosed, by definition, will be what you get by looking at the solution at infinity. Right? As long as this equation is valid, as long as you take this as a solution, we know that there is no energy momentum tensor, because you can evaluate the left hand side of the Einstein equation, right? R mu nu is 0, so there cannot be any T mu nu, clearly. Okay. So T mu nu can be there only in regions where this solution stops being valid. Okay. So let's suppose that this stops being valid for rho less than rho naught. So inside that there can be energy mass distribution, right, which is producing this field. We don't try to calculate the mass distribution by actually counting how many masses are there inside that region, because that's very complicated. We calculate the total mass contained in this system by looking at what kind of gravitational field it produces at infinity. Right? That by definition will be the mass that is contained in this region. Is this okay?
So we are working with natural units. And when we actually evaluated at 0, 0, we had -2π by c square.
That's right, yes.
So if we go out of natural units, the constant that we have evaluated here would actually be c square times this value.
C square.
Yes, that is true. Maybe yeah.
By C square.
Or will the
dm
c
by
square
c
is
square.
considered as c?
Yeah. This will be small anyway, right? Because h naught not is small, you know. Right? Yeah. So I think this h naught is -2π over c square. Yeah. So this will be gm over 2 gm over c square. Is this point clear?
Sir, I have one more.
Yes.
So then, in addition to the question that I asked, like the gravity can be solved by the EM field also. So supposedly you have that test particle at the center, which hypothetically say doesn't carry a rest mass but carries some finite charge Q. So
Yes.
in that case, this M would be some equivalent dimensional quantity that is equivalent to mass.
Yeah, except that if it carries charge,
Just
right,
but no-
then the electromagnetic field spreads out everywhere, right? Then the energy momentum tensor is not zero anywhere, right? So this the equation that we have solved is no longer the correct equation. So there is a solution that is known, right, in the presence of spherical symmetric electromagnetic field. So that's basically a coupled system of gravity and electromagnetism. Yeah, so that you can also solve, and the solution is known. Okay, but it will not be described by this solution, because this solution
T mu is not.
T mu is zero outside at least that region, right?
So assume I solve for outside the sphere and inside the sphere. Then there should be a condition like a boundary condition which I will put between the two surfaces, right?
Yes.
But here your metric is perfectly defined and now there is nothing to, no freedom to have such a condition, right?
No, there will be freedom, because the point is if there is really a sphere, right, then at rho equal to rho naught, that's the radius of the sphere, this is no longer the metric for rho less than rho naught, right? So for rho less than rho naught, we will solve for the metric, and then you have to match with this.
So everything will be fixed on that metric, nothing on this one.
Well, you have to adjust the C, for example, right? Yes, otherwise everything will fix on that metric.
Yeah,
Yes, exactly.
You have fixed the C even by using
The total mass. Yeah.
total mass.
Yeah, exactly. So then everything has to be fixed on that metric. The metric that is in the interior.
So there we will
Meaning it's like this part is not very different from Newton's gravity, right? Think of Newton's gravity. Okay? There also you fix the field outside is minus C over rho, that you cannot change, right? Okay, and the C being the total mass, that also you cannot change. Right? So there when you integrate it in the interior, you solve the thing in the interior, and then you match the boundary condition to find out how the field will be in the interior.
So here we use the boundary condition at infinity, there we will use the boundary condition at the meeting point.
Yes, exactly. Yeah. Let's see, here we are assuming we are using the boundary condition that these should go to 1, right? That's our starting point. Right? Then you evolve it in the interior. Now we will put the boundary condition on the surface of the sphere and then evolve it by using the energy momentum density.
So can you tell us what all boundary conditions you will need to find the metric?
In general, it is very hard problem in Einstein's gravity. Okay, but for this particular radial spherical symmetric problem, you need the boundary condition at infinity, right? Which are set into asymptotically flat metric
Yeah, this is one boundary condition that should be
and total mass, which fixes this coefficient. Okay. With that you can start evolving inside in the interior. And then if there is a mass distribution in the interior, you have to match the boundary condition there.
But that thing, it's like you have two conditions at rho, which is actually an infinity kind of thing, where you have a really a flat space, and then it's little bit when you are a little bit near to infinity but not infinity, and then you are putting C to that thing. So there are two kind of boundary conditions at infinity. I'm not.
Well, one you can change by scaling scaling t, right? The fact that it's eta mu u, you can change. If you change t to t times constant, right? That constant can be changed, for example, right? The g naught did not approach 1.
Yeah.
Okay? So eta mu nu, the fact that it approaches eta mu nu, that you have fixed by
No, but metric will be flat here.
metric will be flat, exactly.
That is one boundary condition.
Exactly, yeah.
And another boundary condition is again you are putting it at near infinities. Right?
Because even in the absence of mass, the flat metric is a solution, right? Okay. So there is some more information that you have to put in, which says that there is a point mass.
Yeah, but you are putting the information again at infinities. So
Yes, that's right. So two boundary, but it's a second order differential equation, right? I mean, even if you have convert everything to a radial equation. See, we consider Newton's gravity, right? The same problem there, right? Phi, you have to set phi equal to 0 at infinity, and that's something your choice. You could have taken phi to be a constant, but you have to set phi equal to 0. Then you fix the coefficient of 1 over rho term by identifying that constant with the point mass, right? So two conditions you need at infinity, right? The constant part of phi and the coefficient of 1 over rho. With that, you can start radially evolving down. And then, if you hit a charge distribution, you change your equation and you match the boundary condition at that boundary, right? It's a second order differential equation, so you need two boundary conditions. And those two boundary conditions, they will come from how what phi is and what d phi d rho is at that junction, at that interface, right? With that, you start evolving to the second order differential equation.
Can you sort of say it like, the relation between a volume integral and a surface integral? Everything happens.
No, in this case, the only way to define things is through surface integral. Okay? Because Einstein's theory is non-linear, in general, doing things in the volume integral is hard. Okay, and that's because gravity can produce its own mass, right? So what mass you put at the origin is not a relevant question. Okay? What is relevant question is what mass you see at infinity. Okay, that is unambiguously defined. If it is a linear equation, right, like in Newton's theory or in electromagnetism, there is a direct relationship between what point charge you put at the origin and what the surface integral is. Right? There we had a choice of defining the charge either by doing a volume integral or a surface integral. In this case, writing it as a volume integral, okay, particularly when there are singular configurations, is hard, but doing it as a surface integral is easy. Right? So the correct way to define charges is always by doing a surface integral.
Say gravity can produce its own mass.
Pardon?
Gravity can produce its own.
Because the point there is no well-defined separation of how much is the gravitational energy. Right? Suppose you have a gravity wave propagating through this, right? It will produce its own gravitational field. Now, for many purposes, it's useful to attribute certain amount of energy momentum tensor to the gravity wave. Okay? So in other words, when you write down this Einstein's equation, R mu nu minus half R G mu nu equal to T mu nu, right? You can take part of the this R mu nu minus half R G mu nu on the right hand side and interpret this as the energy due to gravity. Okay? Because it's not linear. Okay? See, it's not a linear equation. If it is a linear equation, then all the linear part you keep on the left hand side. Okay? Whatever appears on the right hand side is going to produce a source for this. Okay? But because it's a non-linear equation, okay, sometimes it's useful to keep part of it on the right hand side and think of that as a source. Okay? I mean, it's like in electromagnetism, right? You have electrons and photons. Okay? You think of the electrons as source. You arbitrarily, when you write down the equations, right, d mu f mu equal to j mu, you give some special role to j mu, right? But after all, the equation is d mu f mu minus j mu equal to 0. What allowed you to separate it? Right? Or what motivated you to separate it? Right? Because that is the equation that you get from the action is d mu f mu equal to j mu. Here, what motivates you to separate it is because the d mu f mu part is linear, okay? J mu is non-linear, and it's a convenient thing to separate it out. But if you define the charge density by doing a surface integral, then you don't need this separation, right? You just define your electric charge as what you get by integrating the electric field at infinity.
Mass is only defined locally in the inertial field. In that some sense, we are
No, because that is point mass. Like if you have phase particle mass, right? If you have sun, right? How will you measure the mass of the sun by local inertial field? Yeah, I mean we have to. I mean the mass of the sun you define by seeing what kind of gravitational field the sun produces at infinity.
So there is
I mean the sun is still sufficiently weakly coupled so that you can actually go inside the sun, measure each of its atoms energy and then add them up.
Yes.
Okay? But yeah, this is not always possible.
Definition of mass is different.
When gravity is very strong, right, as we will see, then it's not possible to just go inside and count the masses and come back and declare that is our total energy. Right? It's easiest to just define energy density by the surface integral.
The Einstein's equation itself suggests that we can only understand what is the mass behind it, which is producing the mass energy tensor, is the change in the geometry.
Is that?
Is the change in the geometry. that is g mu equal to t minus 8 pi t mu, that the mass inside the t mu.
It's not specific to Einstein's equation. If you have a non-abelian gauge theory, it's the same problem. Any nonlinear system, when you try to define a charge, you define it by doing an asymptotic integral. Okay, because you cannot always separate out the source from the thing, that field that is being produced. Okay, so the main difference is that gravity is non-linear. Okay, so in a sense, the gravity can source its own. Gravity acts as its own source.
So the equations are non-linear because means if there are say two solutions.
Yes.
The superposition of them
Is not a solution. Yeah. Okay. So let me now put this back in and write down the solution. Is minus 1 minus 2 gm for rho. It is square plus 1 minus 2 gm inverse rho square. Now this metric, this seems to have a problem, and the problem is that it seems to be singular at rho equal to 2 gm. Okay? This vanishes, this vanishes. Now if the mass distribution, okay, that is actually producing this field, okay, had been sufficiently spread out, so that rho naught, that what you have been calling rho naught, right, the radius inside which the solution is not valid anymore because the mass is distributed inside the radius. If rho naught was larger than 2 gm, then you have no problem. Okay, at least you have no problem with this, because if rho naught is larger than 2 gm, you can only trust this solution outside rho naught. Okay, once you reach rho naught, the equations change. Okay, and then you have to analyze your equations and see what the solution is. Okay, which may or may not have singularity, we don't know. At least this by itself will not tell us that there will be a problem necessarily in that case. And sun is like that. Okay, for the sun, if you want to calculate what this radius is, it's much smaller than the radius of the sun. Okay, so the most of the mass of the sun is distributed outside this radius 2 gm, where the solution breaks down. So for sun or ordinary stars, it's not a problem. But I should say that this solution is known as the Schwarzschild solution. And this radius 2 gm is called the Schwarzschild radius. And it's an important question that given a massive object, okay, which you can take to a spherical symmetry, given a massive object, the radius, actual physical radius of that object is larger than its Schwarzschild radius or smaller than its Schwarzschild radius. If the physical radius is larger than the Schwarzschild radius, then you don't have to worry necessarily about this problem that the metric is becoming singular. But if the physical radius is less than the Schwarzschild radius, then you have to worry about what the interpretation of this is. Okay, what is the singularity telling us?
Which object is this? Is the
Well, the object for which the physical radius is less than the Schwarzschild radius, those are called black holes. Okay, that's the definition of a black hole, that for black holes this metric is really physical. This singularity that you see here, okay, has some physical effect. Okay, we'll see that this is coordinate singularity. Okay, you can remove this by coordinate transformation, but nevertheless it will have many physical effects which we will discuss.
the horizon.
Yeah, so this rho equal to 2gm is what we call the effect horizon. Okay, but for now we will study a more mundane issue, which is that let's suppose that we have this solution. We don't care at this stage whether the physical radius is less than the Schwarzschild radius or larger than the Schwarzschild radius. So we take this solution as given, and we study the motion of a particle, of a test particle in this background, and we only study those kinds of trajectories which lie outside the Schwarzschild radius. Okay. If the object actually has some physical mass distribution, then the trajectory should also lie outside the physical mass distribution, because we will be using this solution to study the trajectory. Yes. So the point is, so you have this object here, spherical object, right? It has some radius, which is the region beyond which we don't know at this stage how to interpret is either the Schwarzschild radius or the physical radius, whichever is bigger. Okay. If it's physical radius, then the solution itself will change. If it is Schwarzschild radius, then the solution will not change, but we still have problem interpreting what this singularity means. Okay. But we will be considering the trajectory of a particle like this, okay, which do not go through this boundary. Okay. Whether it's the physical boundary or whether it's the Schwarzschild radius depends on which one is larger. Which means that we will basically take the solution as given, trust it, and we see how the test particle moves in this background. Is this point clear? Okay. So this will be relevant also for the sun. Okay. For the sun, we will accept that the physical radius is larger than the Schwarzschild radius. Nevertheless, okay, the metric of the sun is given by this outside the physical radius of the sun. Okay. So if you are going to study our motion, okay, or the motion of another something else around the sun, then you have to use this metric. Okay. As long as the trajectory doesn't go in the interior of the sun.
The mass of the test particle does not affect the.
Yes. So we will take the test particle to be small mass so that it doesn't affect the geometry. So which basically means you have to study geodesics in this background. Okay, because since there is no other force, okay, the test particle will move along a geodesics. So you have to see what the geodesics are in this background. Test particle motion in the background. So that, of course, we know what it is. The geodesic equation is d2x mu. I'll use u. d square plus gamma mu sigma. So all you have to do is to calculate our gammas for this background and substitute. Okay, and if you have done your exercise, you would have already calculated gammas, because after all you have to calculate the r's, right? Okay, and for that you have to calculate gammas. So let me write down the results. The exercise. Okay, you would have already done by calculating the gammas. So d2 of t is d2t square plus. Okay, I'll not write down the arguments
Equation of motions can
pardon
equation of motions can be directly derived from the Lagrangian.
yes you could, but you can also you have already written it, right? And if you have already calculated your gammas, you can just substitute here.
The other gammas can be calculated in in other fashion, like deriving the equation of motions. Like G
Well,
mu
that is probably harder. I mean, gamma mu you have already defined in terms of G mu and this derivative,
if
right?
we just take a variation, isn't that?
Yeah, you have to take the variable, you have to take the variation as to all the variables.
Yes, yes.
Right? Yeah. Other way you can calculate this. There are more terms here. Okay. So if you have calculated your gammas, it just requires substituting the gammas from whatever you have calculated, and I am using notation of psi and chi, but of course we keep in mind that we know what psi and chi are. Now you can see that this problem should be similar to what we do for central force problem, right? Because we are studying the motion of a test particle around a massive object. So you should, in some sense, okay, some of the things at least should be analogous to what we do in central force. Okay, that you have a central force and you have a particle moving in that. Now, if you remember, the way we first solve central force problem is that it's useful to think of the motion in a plane. Okay, not in a three dimension, but motion in a plane. And the reason that we can take the motion in a plane is because of the conservation of angular momentum. Okay. So there is a similar conservation law here, okay, which you can derive in very different ways, okay, including starting from the Lagrangian. But we will try to use a more direct analysis based on the equations of motion to argue that a similar simplification can be carried out here. Okay. So let's look at the problem in the following way. Okay. That we start the particle. So to solve this problem, of course, you have to give an initial condition. Okay. So that means you have to fix the location of the particle at some fixed time. Okay. Suppose the initial condition has been given at some time t. Okay. You have to fix the location of the particle and you have to give its velocity. Okay. D theta, dt and theta. Is this clear? Okay. Now let's first look at the choice of theta. The claim is that you can always choose theta to be pi by 2 by orienting your axis. Okay? Because after all, if you remember x1, x2, x3, the relationship, it is the same relation as we have in normal Cartesian coordinates, right? R sin theta cos phi R sin theta. Okay. So think of it geometrically, don't think of it as actually measuring metric or something, okay. But in the x1, x2, x3 space, this means that you can always choose even any point in this x1, x2, x3 space. Okay. You can always orient your axis so that the initial point is on the equator. Is this clear? Right, which means x3 is equal to 0. Initially, okay, we have x1, x2, x3 and t. Right? Let's go back to the x1, x2, x3 and t where the rotational symmetry is easier to visualize. Okay? If you go back to the x1, x2, x3 and t coordinate system, okay, the claim is that the initial position of the particle can always be taken to be x3 equal to 0 by orienting the x1, x2, x3 axis appropriately. Right? It's completely up to you to orient the axis and you change your axis orientation so that you are sitting here on the equator. Is this okay?
Since it's only a simple rotation, the equation of motion is only.
Yes, equation of motion on the metric is invariant under rotation, right? Okay, so even if you had rotated and then started using the metric, you will write exactly the same metric. But you want to now argue more. We want to also argue that the initial velocity. Okay, so that after you have fixed it on the equator, okay, we have not exhausted all freedom of rotating the axis. Okay, we still have some freedom left, and the next claim will be that by using that residual freedom, okay, of rotating the axis, keeping the fact that the thing is on the equator, we can make the velocity also, the angular velocity also along the equator. Okay, let me explain it. So you start from here. Okay, that much we have accepted. Now we can throw the particle in an arbitrary direction, right? It will have some radial component, some angular component. Okay, angular component from here could have been here or here or here or so on. This is okay? Claim is that whichever way the angular component is, we can always orient our axis without destroying the fact that it's on the equator, okay, so that the angular velocity is along the phi direction. Radial direction velocity of course is there, but the angular velocity is always along the phi direction. Is this obvious?
Means phi direction is on top of its own.
Phi direction means that the phi, the d theta dt is 0. See, from here, imagine that you go in this direction, right? Then it has a radial component, this is the theta component, and also the phi component, right? The claim is that the angular velocity can be chosen in such a way so that the d theta dt is 0. Is this obvious or should we?
d theta dt means we are using d theta du or dt.
It doesn't matter, whether theta dot, whether to measure with respect to u or t. If it's 0, it's 0, right?
Yes.
Okay. Think of it geometrically. Okay. Here is the center. Okay. Don't worry about the metric or anything. Okay. Okay, this is pure geometry in the Cartesian geometry. Here is this origin. Okay, here is a part in the initial position. You throw it in some direction. Okay? So that means that you think of this as a line, tangent vector. So using the origin and this line, you can draw a plane. Yeah, there is always a plane in 3 dimensions which passes through which contains a given line and a given point. Is that clear? Suppose you are given a point and you are given a line. Okay, you can always draw a plane. Okay, first draw a plane through that line. You can keep rotating the plane and rotate it till it passes through the point. Is this okay? So that means that you can always find a plane. Okay, so that the initial velocity lies in the plane, okay, and the point, the origin, passes through the plane. Now you choose your z-axis perpendicular to that plane. Okay, if you choose your z-axis perpendicular to that plane, that means that the initial position of the particle is on the equator. Right? You draw a sphere now. It's on the equator, and the initial velocity is only along the phi direction. Right? Because it's in the plane. Initial velocity is in the plane of that you have drawn. So which means that it is always possible to choose your initial axis x1, x2, x3 in such a way that in the initial condition theta is equal to pi by 2 and d theta dt is equal to 0. Is this okay? So this is what you are going to use.
So I'm first rotating such that my particle lies on the xy plane initial position.
Yes, you can think of it that way, but you think of it in the second way that I said. The think of the particle is here and there is a line passing through the particle which gives the tangent to the velocity. Right? Now draw a plane, okay, through that contains the origin and that line. Okay? Declare the z-axis as the one that is perpendicular to that plane. Okay? It doesn't matter now how you choose the x1, x2 axis. This guarantees now that the initial position is on the equator, right? Because the z-axis is perpendicular to that plane. Right? That's the equatorial plane. Initial motion is also around the equator, in the equatorial plane. Right? So which means only the theta, the phi derivative and the r derivative is non-zero, but there is no theta derivative. Okay? So the claim is that by using rotational freedom, we can choose theta equal to 0 and d theta dt or d theta du, whatever you want to call it, equal to 0 initially, which you can take to be equal to u. Pardon? Theta equal to 5 by 5. Thank you. Theta equal to 5. Now let's suppose you have chosen the initial velocity and position this way. You also have to fix, of course, the initial value of rho, right? How far from the origin you are in. Okay, the initial velocity in the rho direction, radial velocity, and so on. So all those you have fixed, suppose here specified, and you have found a solution. Okay, that means you have found how theta changes as a function of u, how phi changes as a function of u, how t changes as a function of u, and so on. Now let's look at this equation over here. Okay, we already have found a solution, which means that this d phi du is some known function of u. D rho du is some known function of u. And theta satisfies an equation of this form. Okay, theta has also been found, but let's just think of this as an equation that determines theta. So this is a second order differential equation for theta. Okay,
With this condition, two terms are 0.
Yes. So we'll come to that. So the point is that we think of this as given functions, okay, and just think of this as a second order differential equation for theta. So if we specify the initial value of theta and the first derivative of theta, then the solution is completely determined. Right? If you can find one solution, that means that is the solution. Okay? Any solution that satisfies the correct initial condition is the solution. Now the claim is that theta equal to pi by 2 is a solution to this equation. Why? Because theta equal to pi by 2 will make this 0. Because this is cos theta here. Theta equal to pi by 2 will make this equal to 0 because infinity is 0. It satisfies the initial condition clearly. Okay. And theta equal to pi by 2 will also make this equal to 0.
The solution itself is theta equals to.
Yes. So theta equal to pi by 2 is a solution to this equation which satisfies the correct initial condition. Okay. That means that is the only solution. Because if you think of this as a second order differential equation for theta, then once one solution is there, it is the only solution. Is this okay?
So it will remain on that plane.
So that means it will remain on that plane. So this is the analog of what you see in what you do in standard central force problem. Okay. That it is possible to orient your axis so that the motion is always remaining on the equatorial plane. Okay, it doesn't mean that you are focusing on some spatial motion. Any motion in this background can be thought of as in the equatorial plane by appropriately orienting your axis.
We need to know rho and phi. Rho and phi because if we know.
Yes, you need to know rho and phi. Suppose you have given rho and phi. Suppose you have solved the equation, right? Then I am thinking of it in the following way. That let's imagine we will prove by contradiction. Okay? So suppose with theta, with these two solutions, given these two and given other boundary conditions, you have found a solution. Okay? For rho, phi and everything else. Okay? Now substitute for phi that solution. Substitute for rho that solution. Okay? Don't do it for theta. Okay? Now think of this as a solution for theta, as an equation for theta. Okay? Viewed that way, this equation should have a solution, right? And this should have a unique solution if the initial conditions for theta are fixed. Okay? And now I am saying the initial conditions for theta are indeed fixed. Okay? So there is a unique solution to this, okay? And that solution is theta equal to pi by 2. Okay? This doesn't depend on what this function is and what this function is. Is this okay? So this shows that you can focus on a motion which is where theta is equal to pi by 2 all through, and that clearly simplifies things a lot. Okay, so we'll now rewrite the equations under that condition.
Sir, is there any way to figure out that this will be true? When we set these values,
Yes.
we did it with some motivation.
Well, we had some intuition that for central motion the motion in the equatorial plane is the correct one. Okay. If you want to prove it systematically, okay, you have to do what you do for central force problem. You have to write down all the conservation laws. Okay. And with the conservation laws, you can basically integrate the system. Right? You don't have to assume that the motion is in the plane. Right? For any motion, okay, once you use correct conservation laws, you can always reduce to a one variable problem and integrate. Okay, but that's what you do in more advanced approach. But when you first solve the central force problem, it's easiest if you just focus on the equatorial, the planar motion. Okay, but the point is that planar motion is not a spatial motion, right? The important point is that any motion is planar in central force problem. Okay, so as I said, if you want to do it in a more advanced way, you have to actually write down the conservation laws. Okay, and based on that, you can actually integrate the system exactly as you do in classical mechanics.
I'm asking that looking at this equation of theta, can we say a priori, at least guess a priori?
Well, the point is, if you just look at these equations, right, then it's not completely obvious that there is a rotational asymmetry in the problem, because the rotational asymmetry is hard to visualize in the theta phi coordinate system. But on the other hand, if you look at this, right, then if you examine it carefully, you see that you can make this vanish, satisfied automatically by using this, right? And hence, if you use this as the initial condition, then this will be satisfied. What is not completely obvious from this set of equations is that you can always make the initial condition this way. Okay? For that, you need the equation from rotational symmetry. Okay, so with this, then this equation is automatically satisfied. Okay, you don't have to do anything about this equation. This equation doesn't simplify because it didn't have any theta dependent term anyway. But these two terms simplify, right? So let's write down this equation and the phi equation.
Rotational invariance in three-dimensional space tells me that I have three Euler-Angle parameters to set my position.
Three
Euler-Angle parameters to set my coordinate system.
For Euler-Angle parameters, label the rotational transformation.
Yes.
Yes.
So I can choose three Euler parameters to set this theta equal to pi by 2 and the initial direction of the velocity.
Yes, except that if you use the theta phi coordinate system, then the action of the rotational symmetry on theta phi is complicated.
Yes,
right?
absolutely.
That's why in the x1, x2, x3 system it's clear. Right? What you are doing. In the theta phi coordinate system, you have to do a little more work. Right? To see that you have to first see how the rotational transformation acts on theta phi, and then you have to show that by choosing the rotation matrix appropriately, you can always bring theta to pi by 2 and d theta d equal to 0.
Actually, I am asking this because setting a point on a plane is using one Euler angle, and setting the first vector, that is the velocity vector, to a plane is using two Euler angles. So in
Yes.
principle, we can see that using three Euler angles, we can put.
Well, counting parameter always doesn't work, right? Because then third Euler angle you cannot use to do anything more, right? So you have to make sure. Yes, see, counting parameter you can see you have 3 degrees of freedom, so you should be able to set two things to equal to whatever we like, right? But having parameters doesn't always mean that you can do it, right? So you have to actually demonstrate that you can do what you want to do, right? And so in Cartesian coordinate it's simple, right? It's clear what you are doing.
We can also take a rho equal to constant hypersurface and then see that the metric becomes Minkowski.
Metric becomes.
I mean, if we take the rho equal to constant hypersurface.
Yeah, then the metric is like that was clear.
Then Minkowski metric. Sort of.
Well, not really Minkowski metric.
No, not t equal to constant, just rho equal to constant.
Yeah. So then this minus d rho square, but then the theta phi is like a sphere, right? It's not, in fact, rho equal to constant hypersurface is not Minkowski, right? Because it's like the time coordinate times a sphere.
Minus psi rho dt2.
Yes, so that
This
gives
can be
constant times dt square. Right?
that is another time coordinate you can define.
That's it, yeah.
dt dash square plus rho square d theta.
But that's not a Minkowski space, right? Because rho is constant, means rho equal to rho naught, right?
No, in Minkowski space for a constant time.
Yeah, I mean that the point is then you cannot arbitrarily take subspaces, but that's not necessary, right? I mean here all you are trying to see is what you can do with rotation, right? So you don't need the metric, right? Because this is just a question of whether by rotation you can set certain initial condition, right? So for that you just use the x1, x2, x3 and see what you can do in the x1, x2, x3, right? Because the fact that this whole analysis doesn't depend on the metric, right? All you are saying that in the x1, x2, x3 coordinate system, you know that you can choose the motion in a plane, right? That initial condition you can choose so that the initial velocity vector and the origin lies in a plane, and that is enough to show that you can always bring the initial point on the equator and the initial velocity around the equator, and you can translate that back into theta phi coordinate system.
This means there exists a coordinate transformation which will bring the actual solution to this form.
Exactly, that's right. So this if you now forget about all this other argument and come back directly to the metric in this form, this shows that given any solution, you can make a coordinate transformation, not a coordinate transformation, a rotational transformation, which these are the form of the metric, just a rotational transformation, which brings the trajectory in this equatorial plane. Yes.
So mathematically, theta 0 and d theta d 0 also will give or fix the solution.
Yeah, theta equal to 0.
It's like coordinate singularity.
Yeah, is
Phi is not different.
well, it's not coordinate singularity. Yeah, theta equal to 0 is like the north pole, right? And there, it's not clear what is the meaning of d theta d.
So that equation will diverge. What theta theta equals to 0 if we choose.
Yeah, this equation of course will divert. Yeah. So, I mean, what plane will you consider then, right? If you take theta equal to 0 and d theta d equal to 0. Right? In particular, theta equal to 0 will not remain theta equal to 0. It's clear. Right? If you are at the north pole, and if you give a velocity in the phi, if you are at the north pole, right? And if you are giving, let me put it this way, that if you are at the north pole, okay, and if you are saying that d theta d is equal to 0, then it's a very special initial condition. You are putting the particle at rest.
But the fourth equation will suggest that it will remain there.
Yeah, but this is not a generic trajectory. What we are trying to argue here is that a generic trajectory can be brought into this form. What we are saying is that if you set theta equal to 0 and theta equal to 0, it will remain there, right? Which is okay. Okay, that's a radial trajectory. Okay? But that is not a generic trajectory. What we are trying to argue here is that a generic trajectory, okay, a generic initial condition, can be brought into the form of theta equal to pi by 2 and d theta d equal to 0. Okay? You can see in x1, x2, x3 coordinate points, right? If you set theta equal to 0, you are putting it on the z axis. And d theta d equal to 0, that means that you are not putting any velocity at all.
So it's like an unstable equilibrium.
No, it's just that in the initial condition, is the particle at rest, right? You are dropping it, so it will just fall radially. That's a very special motion, right? A generic motion is what we are trying to study here. Right? Theta equal to 0 and d theta d equal to 0 is a special motion which is just radial trajectory.
So any solution cannot be brought into that initial condition form.
Exactly. Any solution cannot be brought into that initial condition form, which you can do here. Right? In this form, if you want to do radial trajectory, then what you have to say is that you have d theta d equal to 0, but also d phi d equal to 0. That will be like starting with a 0 velocity, or only radial velocity. Okay, so let me just write down the equations and then I will stop. So this now becomes d2 rho mu square plus pi prime pi d rho mu square sine square theta becomes 1, so minus rho over pi square the last term is 0 because d theta d is 0. In this equation, the cot theta drops out because this is cosine over sine, that's 0 at pi by 2. So only these two terms remain. d2 phi du square plus 2 over rho phi du du. Then we have to solve these three equations. This one, and this one. Okay, this equation now is automatically satisfied. So tomorrow we will see how to solve this set of equations. Okay. As I said, one systematic way of solving this would have been to first derive the conservation laws, okay, which you could do using Northern procedure in principle. That will simplify getting the solution. But these are simple enough, okay, so that you can actually solve it by inspection. Okay, like the way we do in the first attempt to central course. Okay. Any questions?
So you said we can derive the conservation laws plus how means we have conservation of energy and angular momentum, right?
Oh, we have to write down the Lagrangian for this particle, right? Which you know what it is, right? It's just this object. Integral du square root of g mu nu dx mu du dx mu du, right? This was the Lagrangian. This has time translation symmetry and rotational symmetry. Right? Using that, so corresponding to that, there will be conservation laws, and that we can get by using the author procedure. Right? There is a systematic procedure for deriving conservation laws from symmetries. Right? So once you derive those conservation laws, you can then apply the standard technique to show that the system is integrable and reduce it to the one-dimensional problem.
Yeah, because I was thinking like in classical mechanics, when we invoke this principle of this structural symmetry, we have a notion of a radial force. So we have a notion of angular momentum conservation also.
No, but symmetry comes first. In classical mechanics, when you derive the conservation laws, right? The correct way to derive it is you look at the Lagrangian, which has a certain symmetry. Right? Based on that symmetry, there is a standard technique of Noether procedure to derive the conservation laws, right? Then you interpret this as angular momentum. So it's the same thing here. Right? This Lagrangian will have a symmetry, right? Because of the fact that the metric is in unchanged under certain transformations, like time translation as well as rotation. Based on that, you can derive conservation laws exactly by using Noether procedure, right? The Lagrangian is different, but otherwise it's the same formula. Then you can interpret that conserved charges as angular momentum. Right? For every continuous symmetry, there will be a conserved charge. So you have the conserved charge corresponding to time translation symmetry will be the energy, and conserved charge corresponding to rotation will be the angular momentum. And based on those, you can now integrate the system. Right? You have sufficient number of conservation laws which you can use to integrate, right? And reduce the problem to one-dimensional problem.
So this will depend, the symmetry will depend on the structure of your G mu, right?
Structure of the
G mu, the metric.
Yes, in this case the background G mu has spherical symmetry, right?
Okay.
That's the reason why you have this symmetry. So the reason that this has rotational invariance, that this will be a symmetry which associates rotational invariance, is because of the existence of the concept, existence of a spherical symmetry.
We don't have any general transformation because we have not written a general what is the meaning of a rotation in general.
But you could, right? You know how it acts on x1, x2, x3. So you just have to rewrite things in terms of theta phi.
Okay, we will go in x1, x2, x3 and then show that.
Well, you can go into x1, x2, x3, or you translate the symmetric transformation action on theta phi coordinate, right? Because if you know how it acts on x1, x2, x3, you can also work out how it acts on theta phi. So you can go other way, right? You can either go back to x1, x2, x3 and work from there, or you convert the symmetric transformation laws to the theta phi language. And any other questions?
So the solution that comes from this equation, that asymptotically means that now going tending to infinity, it should look like an ellipse.
Should look like?
An ellipse.
Yes, exactly. Ellipse or hyperbola depending on how the trajectory is bound or not. Yes, that's right.
So, but only in the asymptotic region.
Yes, that's right. Yeah. Well, there will be also a special case which is the motion of light. Because that you don't normally study in the center force problem. Because I mean, there you don't think of the light as feeling the effect of gravity, right? Because you think on a massless particle. Here you have already gone relativistic, so even the light will have certain trajectory, which you will see what it is.